Okay, so good day everyone. Okay, so we will be discussing. So this will be our part 2 for our lecture stresses and beams. Okay, so first we will be discussing about bending stresses. Okay, so we can determine your bending stress by this following formula. Okay, or you can rewrite this as M over S. Okay, so how do we explain this formula? Okay, so we know that this M stands for the bending moment, and then your C, okay, okay, is the distance of the, okay, extreme end, okay, of the beam. Okay, so this extreme end actually it's either top or bottom actually. From the beam, extreme end or top of the bottom of the beam to the neutral axis. And this neutral axis is represented, okay, by the centroid. Okay? And then you have the I. So I is the moment of inertia. Okay. So okay. So in order to better understand, we'll try to draw a beam. Okay, let's have an try to draw a beam. And then let us say that your beam is experiencing a distributed load W. Okay? So we all know from our previous lesson that um, if this is your beam, automatically this okay, the reactions in this, let us say this is A and B, so this is AY and BY. Normally your AX here will be 0 and your AY here, okay, since let us say that the length of this beam is L, so AY will be WL over 2 and BY will be your WL over 2 also. And then for your shear diagram, it will be like this, okay? So since this is a 0-degree curve, okay, this is a flat distributed load, this will be a 1-degree curve here, okay? Okay, in which divided by L over 2 from the left until where it will be 0 moment at L over 2, okay? From the supports and L over 2 here, okay? And it's WL over 2 here, the shear at the leftmost support and negative WL over 2, the rightmost shear at the right supports. Then we have moment, which is equivalent to WL squared over 8. Okay? Okay, so, diba? So, if you try to compute the area of this triangle is equivalent to WL squared over 8, okay? So, if you remember, okay, the change of area in your shear diagram is equivalent to your value at the bending moment diagram, okay? So, 1/2 times WL over 2 times L over 2 is equal to WL squared over 8. So this is how, okay, this is how we compute it, okay. So why is it important that we know the bending stresses along your beam, okay? So one thing is your beam don't have an infinite strength, okay? So in any type of material you use, whether you use steel, concrete, wood, or any other, or any composite material, in combination of those types of material, or even if it is made of another metal other than steel, or any type of construction materials that a thing is made of, there is always a limit, okay? Or let us say, um, there is a time in which your bending stresses on your beam exceeds the limit, in which if it reaches the point, if it reaches some point, it will break, okay? It will cause a break, okay, or failure. So there are two types of stresses in which we need to see, okay, uh, that we will be discussed in this our in our topic, okay, and about stresses and beams. There is bending stress and the shear stress. Under the shear stress, there will be horizontal stress and vertical stress. But somehow, theoretically, your horizontal stress is equivalent to your um, vertical stress. Here, we should concentrate more on bending stress, okay? So, as I have said, there is a time in which your beam will experience an excess of bending stress. And if it exceeds its allowable bending stress, then there is a possibility that it will break, okay? It will break. There is always a limit, okay? And then, when it comes to your beam, actually, okay, at any point on your beam, okay, let us say at this point, and at this point, the shape of your bending stresses are not uniform, okay? So probably at this side, the bending stress will have a shape like this, okay? It's okay, so it will have a not uniform bending stress along your beam, okay? So possibly, okay, so since it is experiencing a downward load, or a downward gravity load, so let us say that the bending stress diagram of this point will be like this, okay? So at the top will be negative, and at the bottom will be positive. And then at this point, it will grow larger, the value. So this will be negative and this will be positive. So your negative is compression, okay? And then your top will be in tension. And also, it will experience, let us say, at the midpoint, since the maximum moment is at the midpoint, so it will experience the maximum stress, okay? So it will increase. But somehow, they will have a certain neutral axis, a uniform certain neutral axis, okay? It depends upon the shape of your cross-section area, okay? Your cross-sectional area, for example, is a rectangle. So if that is the case, it has a dimension of a side B and depth H. So your neutral axis or depth, okay, will be H over 2, which means that you will have two different values of your C, okay? So this will your C will have two different values, okay? We have C C top, and then C bottom. Okay? So if that is the case, you will have two bending stress. Okay? So this will be automatically your C top, and then this will be your CB, C bot. Okay? Let us say C bot only. Okay? In order to conserve. Okay? So I hope you can see it properly. Okay? C top and C bottom. Okay? So do not worry. We will discuss it. Okay. So by using these formulas, we can actually compute. We can now actually compute our bending stress. Okay. We can now compute our bending stress using this formula. Okay. So maybe we'll have another, we'll try another board for this. Okay. So from this drawing, okay, we'll have another board. Okay. So I hope you can see it properly. Okay. Okay. So since we have two different, okay, let us say this is your cross-sectional area, a rectangular one. Okay, since, and its actual bending stress diagram will be like this. Okay, so this is your centroid. Your centroid is located h/2 from either topmost or bottommost portion of your beam. Okay, so from here, this will be from the top. Okay, from the definition, from the topmost support to the neutral axis. Oh, this is your centroid. Okay, so this will be your centroid or the center of gravity of your beam. So we have C top, and then this is will be your C bottom. And let us say this is your shear stress at the middle. Okay, WL squared over 8. Okay, so this is the portion, which means if this is your loading and this is your moment diagram, it means that your maximum moment or your maximum bending moment happens at the middle of your beam. Okay, so more probably the very first, okay, so when it will be overloaded, the very first one to so the very first one to fail, okay, this will be the very first one to fail. Okay, so this will be yours, the center of your beam will be the very first one to fail. In bending. Okay, so this will be the very first to fail in bendings. Okay, so please remember that under this vertically downward load, your top will be in compression. Okay, when we say compression, it is a negative stress. Okay, and at the bottom will be in tension. Okay, so you will compute a two different bending stress. Okay, you have bending stress at the top, which is equivalent to MC top over I, and then we have bending stress bottom, which is equivalent to MC bottom over I. Okay, so you will have two different values. At the compression side, this will be your formula, MC top. And then for the bottom, this will be, you will use C bottom, okay? Please take note, what is your C top and C bottom? From the top of your beam to the center of gravity or your centroid, that is C top, okay? From the bottommost part of your beam, extreme bottom of your beam, up to the center of gravity will be your C bottom. So there will be two different values of your bending stress. And then please take note that, okay, that it will linearly, okay, it will linearly increase from your stress B top to okay, to sigma, to stress at the bottom. Okay, it will linearly increase, okay, linearly increase relative to the height of your beam, okay? So which means from this side, okay, it retains the maximum compression stress at the top, and it will experience, okay, it will experience from at the top, it will experience the maximum um, compressive stress at the top, and then maximum tensile stress at the bottom, which means from the top, and then you go down at any point of the beam up to the bottom, okay, it will linearly diminish up till such a time that at your neutral axis, it will experience stress is equal to 0, okay? So at neutral axis, it will experience a 0 stress, okay? Okay. So at the center of gravity, it will experience 0 stress. So that is how your bending stresses behaves. From the top, it is a maximum compressive stress, and at the bottom, it will experience maximum tensile stress. And it will linearly, let us say, increase, okay? Since from, it will linearly, okay, linearly increase or linearly increase, linearly transition from compression up to tension. Okay? So that is how it is. From compression, it will lower down the value until it will become 0. And then from that 0, at the neutral axis, okay? This is the neutral axis. It will suddenly positively increase, which means it is in tension, okay? This is tension, okay? You might not see it. I have not written it properly, so this is tension and compression, okay? Linearly increase. So negative. So if you will be asked what is let us say the stress uh, H over 4 from the top of your beam, so your computed stress H over 4 from the top of your um, beam for will be computed, okay, through this through ratio and proportion with your topmost bending stress, okay. Okay, so that is how your bending stress behaves, okay.